Greetings everyone. Welcome to the talk Portable Document Flaws 101 at a virtual Black Hat conference in strange times. So, my name is Jens Müller. I'm a PhD candidate at the University of Bochum in Germany. And today I'm going to give you an introduction to our current research, which is a joint work from Bochum on dangerous features of PDF. So in this briefing, we will together dive deep into the less known features of the PDF specification, which can lead to serious security flaws. So in 45 minutes, you may say, well, I didn't know that PDF can actually do that. Okay, so let's put on our Las Vegas sunglasses and let's get started. Also, I'm introducing a new rule for this talk. So whenever I'm going to show you a demo, we are all going to have a drink or a beer together. And there's really going to be a lot of demos in this briefing. Okay, so here's an outline of today's talk. First, I'm going to give you some background information on the PDF document structure and features, so you get a better understanding of the attacks to follow. Then I'm going to introduce our 4 attack classes based on malicious documents that basically lead to denial of service, affecting the host on which the document is processed, information disclosure attacks leaking personal data out of the victim's computer, manipulation of data, and even code execution on the victim's machine. And finally, I'm going to provide an evaluation of those attacks on 28 popular PDF viewers as well as countermeasures for developers. Okay, let's start with some technical background on PDF. I guess we are all more or less familiar with the portable document format, which is basically a de facto standard for electronic document exchange. So PDF was developed in the early 90s by Adobe, and it's an ISO standard since 2008, with the current version being PDF 2.0. According to Adobe, 250 billion PDF documents have been opened in their product in one single year. So I guess it's fair to say that PDF is used in almost every company and institution out there. And it's definitely worth having a deeper look at the capabilities of potentially malicious documents. Okay, let's first have a look at a simple PDF document. So here's a minimal Hello World PDF file opened in Adobe Reader. However, you can also open this very same file using a text editor like VI, for example. And as you can see here, we can actually read and edit the document. There may be some binary parts like graphics or compressed data streams, but the structure of a PDF file is basically plain text, so you can read strings maybe like Hello World. On an abstract level, each PDF document consists of 4 parts. First of all, it's a header, which is only one line containing the PDF version of the document, like 107. A cross-reference, a body, which contains a definition of pages of the document and their actual content. This is the most important part. Also a cross-reference section, which contains an index table defining the offsets of all the documents, of all the objects within that document. And finally, a trailer, which contains some more information, such as a reference to the root element of the document. So PDF documents, they are actually processed from the bottom to the top. Now let's have a look at some related work. So in the past, when talking about PDF security, we have seen various things like, for example, we have seen the recent attacks on PDF encryption and also on PDF signatures, which we both demonstrated last year. But also in the context of PDF, what happens very often is that companies and institutions, they publish PDF documents that are somewhat poorly redacted and thereby reveal sensitive information. This happens very often because content objects are usually not deleted. If the file is edited, they're simply not referenced anymore, and then this allows you to recover previous revisions of a document. A comprehensive study was, for example, performed by Simon Garfinkel and by many others. Also, we have seen some metadata issues that reveal the original author of a document, which is not always desired. So such issues, they were presented, for example, at Black Hat 2008 by Shema Alonso. And finally, we have seen a lot of research on polyglot PDF files that are also valid images or other file types, because the PDF header does not have to start at the beginning of a file, as demonstrated, for example, by Ange Albertini. Now in this talk, we'll focus on insecure features of PDF. And when you study the PDF specification for interesting features, you will quickly stumble upon PDF actions, which are used for various purposes, such as for external links, or to navigate, for example, to a certain page within the document. And even JavaScript within PDF is actually defined as a PDF action. Now, all those actions, they can be triggered using native PDF events, for example, when opening, closing, or when printing the document. And most actions, they can have a PDF file specification as a target, which could be, for example, a URL in order to define a hyperlink. Okay, so we systematically studied the PDF specification for PDF actions and for events that can trigger them. And then we tried to visualize all those findings, resulting in my whiteboard being filled up with a complete mess. So here's a more clean representation. And this is basically the most important slide of the talk, which will follow us over and over again. So we identified 4 special objects which allow you to call arbitrary actions, which is page annotations, fields, and catalog, as shown in the upper part. We call those events. Now, for calling an action, most objects, they offer multiple alternatives. For example, here the catalog object defines the open action event, but also an additional action, AA, as events. And each event can now launch any sequence of PDF actions which are depicted in the middle part. The meaning of the action, we'll come to that later. And the target of an action can be a file handle, or to be more technical, a PDF file specification, which is a multi-purpose object that can be either an embedded file, so a data stream within the document, a local file on disk, a remote URL, or even a network share, depending on the parameters and the context. Now, if a path from an event over an action to a file handle and exists and is not explicitly blocked by the application opening the document, this may result, for example, in file system access or in URL invocation, as we'll see later. But before coming to the actual attacks, let me introduce our attacker model. So our attack scenario is as follows. All the victim has to do is to open a malicious document provided by the attacker. This is a realistic scenario because PDF is generally considered as relatively safe, and even sophisticated users, they download and open PDF files from untrusted sources like email attachments or the internet. For example, invoices, Black Hat slides, Black Hat white papers, and so on are provided as PDF files. Now, once this document, which we denote as the malicious document, is opened, bad things happen, depending on the actual attack. So, for example, denial of service attacks, they would cause the PDF viewer or maybe even the operating system to consume all available system resources or cause them to crash. Note that no user interaction other than opening the document is required for any of the attacks. So in case a PDF application would display a confirmation dialog before performing a certain action, we do not classify this as vulnerable. Okay, let me come to the attacks. So our methodology in finding the attacks was pretty simple. We systematically studied the PDF standard for legitimate features that are critical from a security point of view and which can be abused for attacks. So let's start having some fun with the portable document format resulting in denial of service. Let's start with how to create a PDF infinite loop. So for this, let's first have a look on how the pages object of a PDF document is defined. So a document can have multiple or one or multiple pages or no page at all. And this is usually done using the pages special object within the document catalog. And the pages object has a kids entry containing a reference to each page in the document. Or as the standard phrases it, the kids entry contains an array of indirect references to immediate children of this node. Now, interestingly, the children may be page objects or other page tree nodes. Oh, wait, okay. Interestingly, in other words, the kids entry of a pages object can reference to a pages object itself. So basically to itself, thereby creating a cycle. And this is a no problem of the specification when parsing PDF files. It was already addressed in 2007. So we thought, maybe there are some more issues in the specification. Maybe there are more examples. Let's have a deeper look and study the specification for elements, for objects that allow self-referencing, recursion, and other constructs that may somehow lead to infinite loops. So we came up with the following attack variants. So PDF actions, they allow you to specify an array of next actions to be performed. And basically this can easily result in action cycles. Let me show you a demo. Demos always means we have to drink. What you can see here was an event, an open action that triggers object number 7, which is an action that goes to a certain page in the document. Now there's an entry next action, which refers to object number 7 again, and thereby we have a cycle, right? And then also there are two more object numbers, object 8 and object 9. And they also once again have a next entry, once again referencing to object number 7, and then again we have another cycle. Okay, let's open this document in Adobe Reader, for example. What you can see here is while parsing the document, it jumps from page to page and you can't close it anymore and the CPU goes up, which is somewhat annoying. It's not really bad, but it's somewhat annoying. Okay. And there's lots of other variants without any actions. So using pure structural elements like object stream loops. So PDF object streams, they make 10 other object streams, and thereby once again allowing to craft a document with cycles. Or for example, you have probably seen PDF documents that contain an outline. And the entries of an outline, they can reference to themselves or to each other. And then once again, you can craft a PDF file that when processed creates or parses all cycles and results in an infinite loop. Also, PDF defines type 4 calculator functions, for example, to transform colors. And this may once again allow us to define an infinite loop by defining a recursive function. And finally, in case the PDF application supports JavaScript within documents, well, then infinite loops are super easy to intuit, right? Okay, so the takeaway here is that there's lots of options to keep the PDF processing application busy by forcing it into an infinite loop, thereby consuming all available CPU. Can we also exhaust all available memory? Sure we can. So most of you are probably aware of the problem of zip bumps. So data amplification attacks based on malicious zip archives. So the first publicly documented denial of service attack using a zip bump was conducted back in 1997 against a FidoNet mailbox operator. But not only zip files, but also stream objects within PDF documents, they can be compressed using various algorithms such as deflate in order to reduce the overall file size of the document. Now, such compressed PDF streams, they are absolutely standard and they're contained in most PDF documents in the wild. And now processing applications, they must first decompress those streams in order to display their content, right? Which raises the question if compression bombs based on malicious PDF documents can be built. Okay, here's basically our Hello World example again. Now let's change this. Let's craft a valid PDF file containing a very long string of 10 GB of repeated characters, A, and so on, to be displayed. So this results in 10 GB on disk, resulting in 10 GB in memory, which is no gain for the attacker yet. Let's now compress this content stream. So in PDF, the Flate decode filter indicates that the stream must be decompressed before being displayed. And this results now in a compression ratio of 1 to 1023, which is unfortunately the maximum compression ratio that can be achieved with the deflate algorithm. However, now the PDF file size can be further reduced by concatenating multiple compression filters, which is totally PDF standard to concatenate multiple filters. And we can even do this for a third time, which then results in around 600 bytes on disk being decompressed into 10 GB in memory. So we have a compression ratio of 1 to 18 million, which is quite good. Let's have a demo on Linux this time. This is our standard Hello World file, but you can see that the content is compressed using a triple deflate filter. The length is around 600 bytes. Let's open this file in Evince, the default PDF viewer for GNOME, and it's loading and loading, trying to display the content. And what you can see here is that memory goes up and up and up. Now, actually, this is not a virtual machine. It's my laptop. It only has 8 GB of RAM. So I do now have to manually interrupt this process. Otherwise, my whole operating system will freeze, and I don't want that. And interestingly, you don't even have to open the file. So it's enough to open the contained directory in Nautilus, in the GNOME file manager, or even in Windows Explorer to trigger deflate bombs. Now, this may be problematic, a bit more problematic than the infinite loop, right? Because we can potentially freeze the whole operating system, depending on resource limitation mechanisms, of course. It's still not that bad, because the impact, of course, of denial of service is somewhat limited for end users. But it can lead to severe business impairment if the document is processed on a server. For example, Evince actually uses Poplar in the background, which is a really popular PDF library, which is vulnerable to deflate bombs and is used by various web applications to process or convert uploaded PDF files on the server side. Okay, that's out of scope in this talk, but this can be really bad. Okay, so let's now proceed with information disclosure attacks that leak personal data out of the victim's computer to the attacker, such as, for example, PDF document, form data, local files on disk, or NTLM user credentials. Let's start with how PDF documents can silently phone home. So at Black Hat 2008, Eric Filial showed how to use an open action event to trigger a UI action, thereby resulting in UI invocation in Adobe Reader. Now this path was quickly blocked in most PDF implementations, which will now ask you for user consent before resolving the UI. But what if we just try another parse? Using this path by calling the UI action from a different event, like from the additional actions of a page object, we can bypass existing protection mechanisms, for example in Perfect PDF Reader. We can also use a completely different action, such as the launch action, which we'll have a closer look later, to trigger a URL. So this path actually describes a clickable link in a PDF document. But what Firefox does is it prefetches the URL, which was not intended by the developers because it results in request forgery, right? So in the context of the web, of course, request forgery can lead to further web security related weaknesses. For example, a malicious document that's uploaded to cloud storage that could trigger at least same-site requests, and this could be exploited maybe to perform actions in the context of the user's account in case that only same-site cookies are used to protect against cross-site request forgery. Okay, so I guess it's obvious what we need to do here. We need to test all possible passes systematically. So this means all possible events, all possible PDF actions, and we use the URL as a file specification target. And if you do this really systematically, craft a lot of test cases, then what happens is if we test them in 28 popular PDF applications, 16 of them will resolve the URL in the background without asking for any user consent. And this can definitely be considered as privacy invasive, right? So it could be used, for example, to de-anonymize users like journalists or activists behind a shared mailbox. We don't want that. Okay, next I will show how user input in PDF forms can be leaked to an attacker-controlled server. So PDF documents that can contain forms to be filled out by the user. This is a feature used on a daily basis, for example, for many office tasks like vacation requests and so on. And depending on the nature of the form, of course, this user input can certainly be sensitive. It can contain data like financial or medical records and so on. And therefore the question arises if an attacker can somehow access and leak such information. So the idea of the attack is as follows. The victim downloads a form, so a PDF document which contains form fields, from an attacker-controlled source and fills it out on screen, for example, in order to print it. Note that there are legitimate cases where a form is obtained from a third party, while the user input should not be revealed to this party. For example, text forms, they can be downloaded from all over the web. Even so, you do not want arbitrary websites to see the input data for the text form, and also they have to be manually signed anyway to be accepted by the IIS, right? Now, what if this text form is manipulated in such a way that it silently in the background exfiltrates data without the user noticing and sends the user input data to the attacker's server? How could we do this? Well, this can be done by combining the did print and the page closed events of the catalog and annotation objects within a document together with a submit form action. Thereby all form data, all user input is sent to the attacker's web server once the document is either printed or closed. Another option, of course, would be, if supported, to use JavaScript to submit the form, or you could use other functions defined in the Adobe PDF JavaScript reference to exfiltrate PDF form values. Maybe I should show you a demo here. So what you can see here is that didPrint is object number 5, which is an action, which means after printing, a form should be submitted to evil.com port 8080. Let's start our netcat on port 8080 of evil.com and open the file with Perfect PDF Premium, for example. And this is now a minimal example for a PDF form where the user would enter some maybe sensitive information like, I don't know, hello black hat. And if the user prints a document, in this example we print to some system printer, what happens is that in the background the all user input like hello black hat is silently sent to our server, which is definitely not intended like this. Okay, next let me show you how PDF documents can silently exfiltrate even arbitrary files on disk. We do this by chaining multiple legitimate PDF features together. So how could we achieve this? We do not only have to leak data to the internet, which we have already seen, we also need to read from local files, right? And to achieve this, maybe let's have a closer look at the PDF standard. So we've already seen PDF forms that can auto-submit themselves. However, now the data to be submitted cannot only be a PDF form field value, it can be a reference to arbitrary stream objects. Now, if you study the PDF reference further, you will find a part where it says every PDF stream on its part can reference to an external file. Okay, you see where this goes. Basically, we embed files on disk into the document and then exfiltrate them using the submit form action or using JavaScript to some external URL. Let me show you once again a demo. In this example, we have an embedded file that actually refers to an external file on disk. See Windows WinINI, which is, you know, the Windows standard Windows system file. Let's open the document in Nuance Power PDF, for example. And once the document is opened, silently the content of that file on disk is leaked to our server evil.com, which is pretty bad. And this also works for other PDF viewers. Okay, next one, let me show you how PDF documents can leak NTLM hashes for Windows user credentials and why this works until today. So, in 1997, Aaron Spengler posted a vulnerability in Windows NT on the bug track mailing list, which can be summarized as follows. Any client program can trigger a connection to a malicious Windows SMB server. Now, if this server requests authentication, the Windows client will automatically try to log on with a hash of the current user's credentials. And this is a well-known design problem in the Windows operating system. I guess most of you are aware of this. And what can be done with it? Well, such captured NTLM version 2 hashes, which is the current version, they allow for efficient offline cracking of the user password, for example, using hashcat. And also if you use or support previous versions of NTLM, they are actually trivial to crack, and they can be considered as broken anyway, as shown by Moxie, Marlinspike, and others. Or you can also use NTLM hashes to perform relay attacks and authenticate under the user's identity, as shown by Oshoa and Hamo. Of course, it's up to the configuration of the victim's setup, like password strengths and security policy, if such attacks are actually feasible. Okay, now in April 2018, Checkpoint Research showed that similar attacks can be performed with malicious PDF files. And they found that the target of a go-to action can be set to a network share, and thereby leaking credentials in the form of NTLM hashes. And this issue was actually quickly fixed in Adobe and Foxit. Let's see if we can find some bypasses. What do we need to do? We need to systematically test all possible passes, okay? All possible events. So for example, by using various techniques to access a network share, like by including it as an external content stream, or by using all possible PDF actions that allow a file specification and then use a network share as the string for a file specification. This may allow us to basically bypass protection mechanisms, which works on a lot of years. Let me show you a demo for Foxit. Okay, trivial open action event and action number 5, which would usually be blocked by Foxit. But if you say the file is not going to be opened, but to print it, then this network share will silently be opened in the background by Foxit. Let's use Responder as a malicious SMB server to see if we get any incoming user credentials. And here we go. If we open the file in Foxit, we will see the hash of the user's password. Okay, that's not too good either, right? Our next class of attacks is data manipulation, with lots of sub-attacks once again that allow an attacker to modify PDF form values, write local files on the host file system, or mask the displayed content of a document based on the opening application. Let's start with form modification. So our goal here is to create a PDF document that manipulates itself, or to be more precisely, its form values. So the idea of this attack is as follows. Similar to form data leakage as described earlier, the victim obtains a harmlessly looking PDF document from an attacker-controlled source. For example, a text document. And the goal of the attacker is now to dynamically and without knowledge of the victim manipulate form field data. What's the impact? Well, this could be abused to, for example, get the victim into big trouble by making some wrong fields and get the victim into trouble of tax fraud suspicion, but also maybe to gain a financial advantage, for example, by adding the attacker as recipient of a tax refund. Okay, there are two ways to achieve this. Firstly, we can use the import data action. So form field values that can be set in a document using the import data action, which basically imports form data from an external source, like a URL, or from an embedded file, and overwrites existing document form data. And this action, this could be triggered immediately, maybe before printing, using the Catalogs will print event. And if JavaScript is supported, you can use JavaScript functions to set the content of specific form fields. Well, this method has an advantage because you can first back up the old value and then later on restore the old value, so the victim will not even realize that something has been changed. Let me show you a demo. We have a will print and a did print event. And both of them reference to JavaScript actions. And first of all, we back up the old form field value, and then we set the value to a new string. And after printing, we will restore the backed up value. Okay, let's do this in Adobe. And we have the original value. We print it. In this case, we print it to Foxit, so as a system printer, so you can easily see the result. And what we will see here is that when printed, the modified string is contained in that document or in the printed version, which can be bad in case of, for example, text forms. Can we do some more? Now let me show how PDF documents, how they can write to and overwrite arbitrary files on disk. How to achieve this? So as previously described, the PDF standard enables documents to auto-submit form data to external web service. But technically, the web service URL is defined using a PDF file specification. And this can also be a local file on disk. So this ambiguity in the standard may be interpreted by implementations in such a way that they enable documents to submit PDF form data to a local file and thereby writing to this file on disk. Furthermore, there are various JavaScript functions which are defined in the reference which allow to write to local files. So if successful, this feature can be used to overwrite arbitrary files on the victim's file system and thereby purge their content. Demo time. Okay, we have basically an onClose action. And what it does, it submits a form to drive E with the file name blackhat.evil. On drive E, we don't have any file yet. Let's try to do this in master PDF. Let's close our malicious document again. And then let's see if the submitted form was submitted to a local file on disk. Okay, you cannot write arbitrary content, but you can control parts of the content by changing the form field values. And you can, of course, overwrite existing content, which could be bad. Okay, so the last attack in this attack class is content masking. Now I will craft a document that renders different content in different PDF viewers. This can be used, for example, to show different content to multiple reviewers of an academic paper, or to trick content filters and search engines which now index a different text than the one that is shown when opening the document. To achieve this, we systematically studied the PDF standard for ambiguities. Ambiguities at various levels, at the syntax and structural level, that lead to different parts of the document actually being processed by different PDF implementations. For example, PDF objects before the PDF header or after an end of file marker, they may not be processed by certain applications. Or a PDF file can contain yet another document as an embedded file. And then using some tricks, it may become unclear which one actually to show. Or what about objects with duplicate object numbers or objects that are not listed in a cross-reference table? Also, it's unclear how content streams should be parsed if their length value does not match the offset of the end stream marker. I will show an example in a second. And finally, there are some edge cases on the syntax level of content streams like uppercase, lowercase, and so on. So those attacks or those edge cases, they lead to 33 single edge case variants, and each of them renders differently in different viewers. Just let me give you one example. So a PDF stream usually has to start with the keyword stream and has to end with the delimiter end stream. However, the stream length must also be defined, which can lead to ambiguities. Should I display the red text or the blue text? Okay. So in this example, half of the tested viewers, they respect the delimiter and show the red content stream, while the other half of the tested viewers, they showed the blue content stream based on the length. And now we found 62 further edge cases that, as said, lead to different content being shown by different viewers. And in some cases, only one viewer shows a certain content. However, note that it's also possible to chain those edge cases together within one single document to achieve the same effect. Okay, demo time. So we have some edge case examples, in this case for Adobe, and you see a different string and a different color basically for Adobe compared to Foxit or PDF Exchange or Nitro Reader, which can be problematic in the context where we assume that a PDF document renders exactly the same content and not something completely different. So for example, in the case of a business contract. Okay, this is what you have been waiting for. Our last class of attacks is the execution of arbitrary code on the victim's machine, basically by silently launching an executable from the malicious document. We do this using the launch action. Now, what is the launch action? The launch action is a somewhat special PDF action that, according to the standard, launches an application or opens or prints a document. That sounds interesting, right? The standard does not provide any security considerations regarding this obviously dangerous feature, and it even specifies how to pass command line parameters to the launched application. Therefore, it's somewhat fair to say that PDF offers code execution by design if the standard is implemented in a straightforward manner. So how to test for this? Once again, we use all possible PDF events, this time to call a launch action with the open parameter. And our target here is an executable which is either embedded within the PDF document or provided as a local file. So let's see if in 2020 we still find PDF viewers that do not ask the user before launching arbitrary executables. This is your last time to drink, so make it double. As you can see, simple code execution are by design in Nitro PDF Reader, in Nitro Pro, in PDF Studio Viewer, PDF Studio Pro, and also in some older versions of PDF Architect. So yeah, life can be simple, right? No buffer overflows, no nothing. Simply abusing legitimate features. Okay, let me come to an evaluation so you can see which attacks are actually possible on which PDF viewers. So we tested 28 popular PDF processing applications, basically all PDF applications for the major platforms, Windows, Mac OS, Linux, and web browsers, because they can also view and display PDF documents natively. And if a viewer version like Adobe Reader and an editor version like Adobe Pro was available, we tested both because they support a somewhat different feature set. Okay, now our evaluation shows that 26 out of 28 tested applications are vulnerable to at least one attack. So for example, infinite loops in one variant or another, they were possible in almost any reader, resulting in the application either to hang or to crash. And the same holds for deflate bombs, which are somewhat hard to protect against, if you do not have any strict resource limitations. And using various techniques, we could craft PDF documents that suddenly phone home once a document is being opened in 16 of the tested readers. User input in PDF forms can be silently leaked to an attacker-controlled server for 11 of the tested applications. We were able to silently exfiltrate files on disk by chaining together legitimate PDF features in 6 applications. For 3 of them, however, there are some limitations regarding the file type. 12 applications, they silently leaked the user's NTLM hashes. So we found various bypasses to existing patches, for example, for Foxit. Now, forms that manipulate themselves using the import action, for example, or JavaScript by changing their form values, for example, when printed, they were supported only by 4 readers, even though this is actually a standard PDF ingredient, but it didn't work very often. Okay, but file system access or file write access, so writing to arbitrary files on disk, worked for 2 applications, which is pretty bad. And for 6 viewers, we could craft a document that renders different content in each and every other PDF viewer. For the others, you basically have to chain edge cases together to achieve the same effect. And in 4 applications, we had straightforward code execution based on the launch action. For another 3 Linux-based viewers, this works only in the case of mono executables, so the impact is a bit limited. Okay, now the takeaway here is that virtually all tested PDF applications, they have at least some issues, right? And PDF viewers that only implement a minimal subset of the PDF standard, they're usually less vulnerable. So such a subset without any fancy features, that's usually enough to simply display a document, as shown, for example, by the PDF implementations for macOS and Linux, but also web browsers. Okay, we reported all those issues to the affected vendors back in January. Some of them are fixed and some of them work until today. Now, how would you fix those issues? So I would say to counter infinite loops, constructs that lead to cycles or to recursion, they must be prohibited in implementations, and also ambiguous formulations that should be removed from the standard, which could also help to prevent content masking attacks. Also, why not limiting the resources a single document is allowed to consume, similar to a website in a modern web browser. Thereby, a malicious document would not affect the whole application or the whole operating system anymore. Now, while our attacks do not depend on JavaScript, a lot of native PDF features, they are redundantly implemented in JavaScript, thereby providing an even larger attack surface. So let's remove or restrict JavaScript. And also, given that PDF is supposed to be a format for portable documents, we'd argue that the need to embed really a full programming language is somewhat debatable. Now, finally, and most importantly, secure PDF processing applications, they should identify and cut the dangerous paths in malicious documents. So most of our attacks, they took a path from an event down to a file handle. And if this path was not blocked or required user consent, the attack was successful. Now, many applications, they blocked particular paths, but they failed to block them all because there was no systematic protection approach. Okay, let me come to a conclusion. So PDF is more than a simple document format. PDF is really, really complex, and it's got a lot of dangerous features. Applications that blindly implement the standard, they're somewhat flawed by design. So if you're the developer of a PDF application, be careful which standard features you actually want to include. Also, even in 2020, you can get code execution based on pure logic chain exploitation. Okay, thank you. You can find all the exploit files on GitHub, as well as a comprehensive test suite in order to test further PDF implementations for vulnerabilities. I really hope to see you all next year in Vegas.